So we're going to finish this year with chapter 11, which is chi-squared. Everybody say chi. Chi. That is not chai. This is not your chai tea latte at Starbucks. This is chi-squared. I am helping you when you are going to be in a fraternity or a sorority, because if you look at what the notation is here, here's what it is. It looks like a big capital fancy X. If you look at that and you're like, hey, what's up, chai? They're going to be like, yeah, you're an idiot. So it's chi, and then yes, it is a squared, like a squared sign. So chi squared. So chi squared. You guys like M&Ms?
Yeah.
Okay.
Can
Sure. All right, the M&M and Mars Company states on their website that on average, the mix of colors of M&M's milk chocolate candies contains 13% brown and red, 14% yellow, 16% green, 20% orange, and 24% blue. The one-way table summarizes the data from the sample bag of M&M's milk chocolate candies. All right, so we take a sample of 60. So basically we open the bag and there's 60 M&M's. And this is how many of each color we have. So how could we use this data to test to see if the percent of each color distribution is correct or not? So we could do a 1-prop z-test for blue to see if this is truly 24%. And then we could do a 1-prop z-test for orange. And then we could do a 1-prop z-test for green. And then for yellow. And then for red. Wouldn't that be fun? No. We would get to do 6 state plan do concludes.
Oh.
Woo! That sounds so exciting, doesn't it? So why does that sound like a terrible idea? All right, it's time consuming. That stinks, right? But here's the most, egregious issue, if you will. Here's the biggest problem. So this is the claim distribution, right? 13% brown and red, 14% yellow, 60, blah, blah, blah. That's the claim distribution. We actually get 9 blue. And let's say we did a 1-prop z-test on blue, and we found that blue was okay. That blue was, in fact, 24% of the distribution. And so that one would be okay, right? And then we did orange, but we found that orange was not the correct percent there. It was not the 20% that they claimed. But then we did green, and we found that that one was okay, and yellow was okay, but red was wrong, and then brown was right. What's the problem here? Is their claim distribution right, or is it wrong? It's wrong, but only for some. And so, like, is it right or wrong fully? Okay, so we might get conflicting results. So that can be a problem as well. All right, so how do we fix this? How do we make sure that we don't have to do 6 1-prop z-tests and we don't have conflicting results? We use something called chi-squared. Also, this data is categorical. This chi-squared is what you use when you have categorical data. So we're not technically we're not looking at a proportion of something, and we're not looking at a mean. We're looking at a distribution to see if the distribution is correct or if it's not correct. That's what chi-squared actually does. All right, so the chi-squared statistic. The null hypothesis in a chi-squared goodness of fit test should state a claim about the distribution of a single categorical variable in a population of interest. The null hypothesis will look like this. The claimed distribution is correct. That's literally what we would write. There's not really a notation for this. Now, I could make there be a notation if, for example, I wanted to make this M&M distribution using actual numbers. My null hypothesis could be P sub blue equals 0.24, P sub O equals 0.2, P sub R equals 0.5, 1, 3. So, like, I could do that. I could write each individual one if I wanted to. Or I could just write the claim distribution is correct. Your choice.
Can we do that for the one that we're learning?
Yeah, totally your choice. Your call. So what do you think the alternative hypothesis would be for a chi-squared goodness of fit test?
It's not correct.
Very good. That would be, the alternative would be the claimed distribution is not correct. So again, M&M's claims to have this particular distribution of 24% blue, 20% orange, 13% red, blah, blah, blah. We assume that they're telling us the truth, because why would they lie? It's M&M's. They're great people, right? The alternative is that, they lying, and it is not the correct distribution. Obviously, you could also say that the alternative is that P sub B does not equal 0.24, or P sub O does not equal 0.2, or P sub R does not equal 0.13, blah, 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 blah. You could do that. In this situation, though, I do want you guys to notice that the claim distribution not being correct means that any one of them could be wrong. Maybe just the blue and red are wrong, but everything else was right. But that's not what chi-squared is trying to do. Chi-squared is not trying to necessarily nail down exactly which one it is that's wrong. It's just, is the overall distribution right? Or is the overall distribution got a problem? I don't know where the problem is. It's somewhere in there. But it either has a problem or it does not. Make sense? Whee! Moving right along then. What are we looking for in a chi-squared goodness of fit test? All right, so here's what we're going to look for. We compare the observed counts, the observed counts, number of things. We compare the observed counts to the expected counts to see if a difference is noted. So I'm going to look at, while yes, the M&M company is claiming a percent of each color, I'm going to have to figure out, well, what number should I get in this sample of size 60? And then what number did I get in this sample of 60? And are they different enough that there's a problem? Or was the difference just due to sampling variability? Very good. So, one other thing, again, just to make sure. Testing to see if the overall distribution is correct. Again, we're not going to necessarily nail down exactly which one is wrong. We're just going to know that something's wrong. Don't know which one, but it's going to be something's wrong in there. Yes, you can do something called a follow-up analysis to see which one is wrong. I'll show you guys how to do that later, but for now, we're just kind of looking at, is the overall distribution correct, or is the overall distribution got a problem in it? All right, so let's do some calculations here. So here is our claimed distribution, right? So we took a sample of size 60. These are our observed values. So we took a sample of size 60 M&Ms. We got 9 blues, 8 oranges, 12 green, 15 yellow, 10 red, and 6 brown. So a total of 60 M&Ms. These are the claimed percentages. So what I need to do, what?
It's wrong.
Huh?
You can already tell it's wrong.
How can you already tell it's wrong?
6 is not 13% of 60.
Are you sure?
100%.
Well, you also know that the brown and red aren't equal.
Okay. So what we need to see, you guys already, this is why this is the easiest unit ever. All right, so we're done. We're ready to take the test. Ready?
Yeah.
All right, expected. We need to look at if these are the claimed percentages, how many would I expect to get of each color in a sample of size 60? So, if I have a claimed percent of 24%, what is the expected number of blue that I should get in a sample of size 60? 14.4. Miss Lakey, you cannot get 0.4 of an M&M. I understand that, but we're going to go with that as the expected value. All right, 20%. What is 20% of 60? 12. So I should get 12 orange candies. Did we get 12 orange candies? No, we got 8. All right, 16% of 60 is 9.6. Did we get 9.6 greens?
No.
Nope. All right, 14% of 60 is 8.4. Did we get 8.4 yellows?
No.
Nope. 13% of 60 is 7.8. Did we get 7.8 reds? Nope. And 13% brown, 7.8. Okay, cool. Question for you. Why are those expected values different than what we actually got? Yes. I know, this is exciting stuff. Why are the expected numbers different than the observed numbers? Is it sampling variability, Jonah? Or is there a problem with the claim distribution?
M&M are liars.
That's why we're doing this problem.
I'm thinking it's M&M's liars.
We're trying to see if this is just simply sampling variability or is there an actual problem with their claim? Are the M&M Mars Company leading us down the path of destruction?
Yes.
Obviously. All right, so here's what we do, you guys. This is the best part ever. Are you ready? You're going to do this little calculation. Oh my gosh, what does that little calculation mean? You're going to take the observed number and you're going to subtract the expected number.
And you're going to square it.
And then you're going to square it. Does anyone have any thoughts on why we're squaring it?
It's chi-squared.
Because it's chi-squared. Why would we square it, though? Why not just chi?
No negative number.
Perfect. I don't want a negative number. I want a positive number here. All right, cool. Observed minus expected squared divided by the expected. This is going to give you something called the chi-squared contribution. Wow, that sounds exciting.
Sounds confusing.
No, not at all. All right, so I'm going to take 9 minus 14.4, and I'm going to square that, and then I'm going to divide by 14.4. What do you get when you do the observed minus expected squared divided by expected for the blue? 2.025. Again, this is the chi-squared contribution. You'll understand why it's called that in just a momento. All right, let's look at the chi-squared contribution for orange. 8 minus 12 squared divided by 12. What do you get?
Oh,
1.33 forever. All right, and next, we're going to get the chi-squared contribution for green. 12 minus 9.6 squared divided by 9.6 is 0.6. Is that what you said?
0.46.
Did anyone else get 0.46?
No, I'm not doing the math.
You got 0.6? Okay. I think I heard Ryan say a typo, so it's fine. Yeah, okay. All right. What is the chi-squared contribution for yellow? 15 minus 8.4 squared divided by 8.4 is 5.1857. And the chi-squared contribution for red, 10 minus 7.8 squared divided by 7.8. Chi-squared contribution for red, 0.621, and the chi-squared contribution for brown is 0.415. Everybody good? Okay. Here's what we would now do. We would take each of those chi-squared contributions for each of those colors, colors, and we're going to add all of those together. Add all of these numbers up. Once you sum all of those chi-squared contributions, you will get the chi-squared value. So this is going to be your chi-squared value. I'm sorry. I know, that's annoying. I'm so sorry. I should have lined up my decimals. All right, guys, when you added up all those chi-squared contributions, what did you get?
10.1767.
All right, cool. Here's our chi-square for this problem. All right, now let me do a little explaining for you for just a second. If you look at the big numbers of the chi-squared contribution, which chi-squared contribution was the biggest? The yellow. Why is that chi-squared contribution so large? That is the biggest difference between the observed and the expected value. So in this distribution, yellow was the biggest problem, okay? Which one had the smallest chi-squared contribution?
Red and brown.
Brown actually had the lowest. What do you guys notice about the observed and the expected for brown? They're pretty close, right? They're not that far off. So the closer the observed and the expected are, the lower our chi-squared contribution would be. Let me ask you this. What would our chi-squared contribution be if the observed equaled the expected? It would be 0. Because when we would do the observed minus expected, we would get 0. 0 squared is 0 divided by whatever is still 0. So if you get a chi-squared contribution of 0, it's because your observed and your expected was exactly the same number. Okay? All right. So, why do these numbers matter? The bigger the chi-squared contribution, the bigger the problem with that particular category. So, who contributed to the biggest problem with the category? Yellow. Yellow is the biggest problem with our distribution. So, it looks like if we find that they're lying to us, it might be because of the yellow. Okay? Now, what is this chi-squared? Chi-squared is 10.1767. Y'all ready for this? Listen very carefully. You ready? Listen very carefully to the words that are about to come out of my mouth. You ready? This is the number of standard units that our sample was from what it was supposed to be. Kind of sounds like a test statistic, doesn't it? T-test statistic tells you how many standard units your sample is from what it's supposed to be. Your Z-test statistic tells you how many standard units your sample is from what it's supposed to be. Well, guess what? Chi-square is a test statistic, and it tells you how many standard units your sample was from what it was supposed to be. Now, what was it supposed to be? It was supposed to be, all of the observed were supposed to be exactly what we expected, and therefore it was supposed to be 0 every time. You're hoping you're always going to get 0, just like you were hoping with the T and the Z and all the things, right? It's the same stuff, you guys. Isn't that fun? All right. How do we know if we have good evidence that the claim is incorrect?
It's yellow, a big number.
When chi-square is large, we have good evidence that the claim is false. because that means that what we observed and what we expected was really big difference. That means there's probably an issue with what they claimed it should have been. You got it? Okay. Get ready for this, y'all. This is y'all. Your brains are about to melt. Ready? Here. No, this is so easy, isn't it? All right. Right. No, this. Watch. You're gonna know the answer. We see some fairly large differences between the observed and the expected counts. This is just a bar chart of what we saw. It's just a visual, okay? How likely is it that the differences this large or larger would occur just by chance in random samples of size 6 from population distribution claimed by Mars? What did I just ask you? I asked you for the p-value just now. That question is, what is the p-value? And guess what? We can find the p-value very easily. All right, so to answer this question, we get the chi-squared test statistic, which measures how far the observed and the expected are from each other. Chi-squared is equal to, this is just the formula for what we just did in the chart. Chi-squared is the sum of the observed minus the expected squared divided by the expected. That's like we did that for each color, observed minus expected squared divided by expected. And then we added them all up, so we got the sum. And that was, in fact, our chi-squared value that we just observed. So in our particular situation, our chi-squared test statistic was 10.1767. Is that what it was?
Yeah.
Okay, so that was our chi-square test statistic, okay? And now our final question is, what's the p-value? So let's find out. Isn't this fun? What?
In the calculator, did we put all the given values?
We'll talk about that in a minute. You're getting ahead of me. Calm yourself. All right. What does the value of the chi-square test indicate? Okay, chi-squared is how many standard units the observed and expected counts differed. Okay, how many standard units the observed and the expected counts differed? Okay, again, this is just like T and Z. Okay, chi-squared is just like a T or a Z. And now here's where it gets a little different. Are y'all ready? Are you excited?
Is it not normal?
Is
it not normal?
It's not normal. Oh no, you guys, it's not a normal distribution. What are we gonna do with our
I'm
lives?
gonna cry.
Why are we gonna do that?
I don't know how to do normal now. Anyway.
What is the shape? What is the shape of a chi-square distribution? Anybody want to give it a shot?
Skewed. Right skewed.
It is right skewed.
No way.
How the heck did you know that?
Yes.
That's a great guess. You had a 50-50 shot,
I
either
also
right or
looked at the
left.
picture down
You
there.
looked at the
Yeah,
picture at the
sorry.
bottom. All right. All right, you guys. Chi-square distribution is always going to be right skewed. Please tell me why.
That's great.
Degrees of freedom.
No, but we are going to use degrees of freedom. All right, here's 0. 0's right here. 0 is what would happen if our observed and expected were the same. But why is it right skewed?
Because they're not the same.
Because the
Oh,
closer...
you're not gonna have a-
What?
You're not going to have a negative.
Why can't I have a negative?
Because it's squared.
Because I'm squaring the observed minus expecteds. So I can't ever get a negative chi-square.
Unless you do math wrong.
Unless you do math wrong, and in that case, I can't help you. All right, so it's always going to be right skewed because we square observed minus expected. Okay, so this is cool. Right skewed. Fun, right? Sure. Yes. All right. Great. Please note, chi-squared cannot be negative. And as Ryan so eloquently put it, If you get a negative chi-square statistic, you done goofed. Okay? Don't be doing that. Don't be doing that. All right, your chi-square statistics are going to be determined by their degrees of freedom. Chi-square test statistics are going to be determined by their degrees of freedom. Easy. Categories minus 1. Very similar to a T test statistic. We do N minus 1. This is categories minus 1. For our particular problem, how many degrees of freedom do we have? 5. How many categories did we have?
Categories.
Categories.
6 categories.
Ah, yes. All right.
You got excited.
So we computed our chi-squared test statistic to be chi-squared was equal to 10.1767. Okay, here we go. Before we can find our p-value, we're getting so close to this p-value, y'all. Before we can find our p-value, we have to ensure our large count condition is
Is
met.
it still 30 or are you going to change that too?
Yeah, I'm changing it. All right, here's the large count condition for chi-squared. All expected counts have to be greater than or equal to, anybody want to take a guess?
60.
It's not 30 and it's not 10.
5.
It's 5. It's 5. All of our expected counts have to be greater than or equal to 5. Ladies and gentlemen, is it okay if I open a bag of M&Ms and I get no blues in it?
No.
Well, no, it's not okay because we want the blue, but is it okay in a chi-square statistic for us to open a bag and get an actual observed blue of 0?
No.
Yes! What does this say?
Expected.
The expected counts have to be greater than or equal to 5. It is totally fine that you expect a certain number, but you get nothing. That's fine. But you have to have expected counts greater than or equal to 5. Got it?
Is there multiple
Hmm?
Just multiple rows or just one?
Is there multiple conditions? There are 3 conditions. Anyone want to guess what they are? Random, independent, and not normal. God bless America. Why is it not going to be a normal condition? Bro is not normal. Bro is right skewed.
It's the skewed condition.
It's the large count condition. Random, independent, and large count. I know, you're sad. Rin is now real. So sorry. All right. Some of you are like, what the heck is Rin? Random, independent, and normal. Okay. All right, kids. Can we check, or can we get the p-value? Yes, because our large count condition is met. All of our expected counts were greater than or equal to 5. And so here we go. To get the p-value, this is going to be the probability that we get a value as extreme or more extreme than our chi-squared. We're going to use chi-squared CDF.
It's second bars.
Is it really?
Yeah, it is. And then just go down until you find chi-squares.
Yes.
Oh, I see it. Lower.
Anybody have any thoughts on where we might find chi-squared CDF?
Second bars.
Second vars.
I'm already there.
Chi-squared CDF. Now, your lower boundary will always be the chi-square test statistic because we're always going to go from there and out to infinity. I guess from y'all's perspective, it's from there and out to infinity. All right, so our chi-squared statistic is always our lower, so that's going to be our 10.1767. It's 9.7?
It's 6-7.
Why don't we just run it to 7?
We wrote 6-7 the first time.
Ryan wants to round it for some reason.
I did too the first time.
What's the upper value?
Run it to 10.
I don't know. I don't care. Doesn't matter to me. You know what? Let's just cut it at 2. You want to cut it at 2?
10.1. I'd say 7.
Hey, guess what? Your upper value would always be infinity because you're always going from the chi-squared out to the infinity. Okay? And then, oh my gosh, what is the third thing it asks you for? Degrees of freedom. How many degrees of freedom did this one have? 5. Ladies and gentlemen, hit enter and you will get your p-value, which is the probability that we get a chi-squared as extreme or more extreme than 10.1677. Point what? Point what?
0.07.
Oh my gosh, you guys! What do you think we should do with this p-value?
Let's take this one 4.
We should. Oh, how many?
Because if the chi-square is taking 4, which I think this is 4.
No, I'm gonna stop it too.
0704.
Nope, I'm leaving it.
I'm putting 0.
Sorry. Hey, you guys, what conclusion should we make? Well, our p-value equals 0.07. Did we have an alpha?
Are we throwing away alpha?
It's still 0.5.
It's still going to be 0.05 unless otherwise said. So this is greater than alpha of 0.05. And so what are we going to do?
We're going to keep it. We're going to fail to reject.
We're going to fail to reject the null hypothesis.
So this is still like a statement.
There is not convincing evidence that the distribution claimed by Mars is incorrect. We do not have convincing evidence that they're lying to us. But guys, why was our observed values different than our expected values? It must have just been sampling variability. We do not have convincing evidence that they've lied to us. We just had some sampling variability in our little bag of M&Ms. We just had some little sampling variability. Huh? It's so dumb? I know, right?
No way that's correct.
That's just sampling variability, bruh. What do you expect? Somebody hand counts the number that they're supposed to put in each bag?
Also, it's not brown. It's
Whatever. What questions, comments, concerns, thoughts, feelings do you have?
why do we do the
Are the
conclusion
degrees of
statement
freedom
before
ever
the
going to
rest?
determine the alpha?
Nope, degrees of freedom will never determine the alpha. Degrees of freedom only determine how skewed the distribution is.
Okay, because sometimes in AP Bio, it did determine
Nope.
alpha.
All right, guess what? There is a test for this. This is the chi-square goodness of fit test. There are 3 conditions. They are random, 10%, or independent. I don't really care which one you call it. All right, random. You guys know how to check the random condition, right? You have an SRS of blah, 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 blah. 10% condition is still 10 times the sample size has to be less than the population size. Large count condition. Ladies and gentlemen, why am I not checking a normal condition? This is a right skewed distribution. So we're going to check the large count condition, which is all expected counts have to be greater than or equal to 5. All expected counts have to be greater than or equal to
We
5.
have to write every single expected count.
Yes, ma'am. You do have to write every single expected count. Yes, ma'am. I'm so glad you brought that up. Hey, ladies and gentlemen, check this out. Before we do a chi-square goodness fit test, we have 2 important cautions. You must write the expected counts. Thanks. Appreciate that.
Anytime.
Must write the expected counts in the large count condition. Okay, here's the other one. Use expected and observed counts, not percent. Most of the time, you guys, just like it was with the M&M problem, it's going to tell you that it should be a percent of each particular category. And then you have to take the sample size and figure out how many should you expect in each of those categories. So you will be given percentages in the problem, but you got to figure out how many should you have expected. Yes, ma'am.
Is it always going to be like a proportion problem?
This is not a proportion problem. It's not a means problem. It's a chi-squared problem.
Only one.
Well, there's going to be 3 different chi-squared problems. This is the first one. This is the chi-squared goodness of fit test, GOF test. So that's the one. Next week we'll learn homogeneity and independence. And then we're done. That's all 13 right there.
Wow, the NC exam was ready.
It's right there. All right, kids. Chi-squared goodness of fit test. Goodness of fit test. You will actually find this under GOF in your calculator. Chi-squared GOF. Don't go there now. The null hypothesis will always be that the stated distribution is correct. The alternative will be that the stated distribution is not correct or incorrect. You can write either word, they're the same things. I know, right? Then you find the expected counts for each category, assuming that the null hypothesis is in fact true. Then you calculate the chi-squared statistic. Now, ladies and gentlemen, here's how you're going to actually do all this. You do not have to make a chart like we just made. You're going to use your calculator. You're going to put your observed counts, not percentages. Observed counts are going to go into L1. Your expected counts, not percentages, are going to go into L2, and then you will go to stat, test, and this one is D, and it says chi-square GOF test. I think it says test.
Yeah, it does.
And then it's going to ask you for, only going to ask you for your degrees of freedom, which you need to make sure you did categories -1. It'll say, is your observed in L1, your expected in L2, and then what are your degrees of freedom? Chi-squared is the sum of all k different categories. The p-value is the area to the right of chi-squared under the density curve with k -1 degrees of freedom. K is your number of categories. And finally, here's your picture. Wherever your chi-squared value is, the area that is as extreme or more extreme than that is, in fact, your p-value. And that, ladies and gentlemen, is how we're going to do it. Next week,